Are we live? Yes. We are live. Hello everyone and warm welcome to Func Prog Sweden. This time, for the second time this year, we are at the Kivra office in Stockholm. It's a very nice office. Thank you very much, Kivra, for letting us coming to your nice office here in Stockholm. Thank you very much. And I'll jump straight into it. First, there will be a short introduction by me, Magnus. Then we'll jump into Super Haskell, an introduction to Agda by André. And then after that, we'll do Schema management with Scalameta by Lars. Fun thing, Lars was actually supposed to do this presentation 3.5 years ago, but then Corona came. And now, 3.5 years later, he's finally here and doing the presentation. So it's really nice. It's really nice. Yes, and then in the end, I'll just sum up the meetup. Again, thank you very much, Kivra, for having us here. If you want to talk to people at Kivra, look for people in green. These, but green. Yes. Also, thank you very much, Agda for sponsoring the video stream. And if you want to know more about Agda, go on internet. And then the coming schedule for the rest of the year. 7th of November, we're back with another meetup. And then 5th of December, we also have another meetup. And then in January, we haven't set the date yet, but of course, we'll have another meetup. Yes. If you want to support the Func Prog Sweden meetup, head over to MeetUp and join the meetup community. Very simple. And of course, you should head over to YouTube and also follow, subscribe, do all the stuff you can on YouTube. Google will love you, and we also will love you. And we have also started the Discord channel. Sometimes it's hard to ask longer questions in the YouTube chat. Jump into Discord and you can ask long, tricky questions to the presenters. So, if you have questions during the presentation, just shout out in the chat or in the Discord channel. Or if you're in here, raise your hand and, oh, I have a question, please. Yes. With that, let's get started. First presentation, Super Haskell, an introduction to Agda by André. Welcome.
Thank you.
Welcome, André. And I leave the laptop to you.
Thanks, Magnus.
Yeah, you're welcome.
Yeah. All right. Mic is working. Let's see here. Let's get started. All right. Thanks, everyone, for coming and for indulging my talk. Let me just do a little bit of setup on my phone here. And let's get into it. Let's explore this language that I like to call Super Haskell. So first, just a very short introduction to me. I'm a Brazilian software engineer, but I've been in Sweden for around 3 years. I'm an FP consultant at Agda, working in PureScript these days, actually. And I have a master's degree at Chalmers University in Gothenburg. Did my thesis in category theory and some dynamical system stuff. That was all Agda. I'm not an expert in Agda, though. I want to give that disclaimer. But hopefully I know enough about it to whet your appetite here. So this talk is going to be, I think this is a very rough estimate. That Tilda is doing a lot of heavy lifting there. But just a little bit of philosophy and motivation for Agda, the language, and its underlying theory. And then some code where I introduce the central concept of the language to you, and then we're going to run a very small but real program using it. So why, first of all? Like, why dependently typed types? Well, the way I see it is that there is a true cost to correctness. When we're writing code, when we're doing software engineering, we usually care about whether the code is correct or not. And I see this as kind of two types of work. Like there is the implementing the code, which is writing the body of the function, so to speak. But then there is thinking about the code you just wrote, ensuring it's correct, and verifying that it does what you actually want it to do. These terms are very overloaded, the ensuring correctness and implementing here in this graph. The confidence required to deem a program correct varies. It's depending on the context you're in, you're going to have different criteria. And so does the amount of work in the implementation. I mean, some people are going to find Python exceedingly easy to write code for. Others are going to think the same thing of Haskell or Agda or any other language. And we want to strike the right balance. I think I'm a little nervous. Like in this example, it's like it matters less that your social media website is slower than usual than if your nuclear plant software has an off by one error or something. And we have some tools at our disposal to guarantee correctness. There's tests, which is obviously not complete. You're never going to think of every possible test to verify that your program is correct. There's trust, which is, well, this thing has been around for a long time, and it's worked for a long time, so the probability that it's going to be around and continue working is really high. That's something known as the Lindy effect. Something's been around forever, it's going to stay around forever. That's not always true. I mean, a lot of people here are going to remember the log4j issue. Azon, an ancient Haskell library, had a vulnerability in it that was caught, I think, a couple of years ago. And types and theorems are also not a guarantee that they do what even they say they do. Even their degree of confidence is not guaranteed. I mean, bugs exist in compilers. I think GHC 9.4.1 had a floating point error. And inconsistencies exist in proof checkers. There was an inconsistency was found in development version of Cubicle Agda, which is an extension to Agda, and which basically means you can prove anything if you exploit that thing. So we can never really be sure. But you can obviously increase our confidence. And the tool we're going to be focusing on with Agda and with, what dependent types tries to bring to the table is this idea of bridging the gap between human intention and machine code, like the thing that the electrons are going to fly around in the wires in the way that you want them to. We want to reduce the amount of times that we say, well, I didn't mean that. Right? And the way I think about types in this context is like, you know, there's these kids' toys where you have to place the right shape in the right hole. That's a sort of plumbing. I think much of programming gets down to plumbing. And if you have, so the analogy here is the shape of the hole is the type of the thing you're supposed to put in there when you're calling a function, say. And the surface in which you create the hole is like the type system. So the type system allows you to express certain shapes. Now let's imagine that there is such a thing as putting a correct shape inside of a correct hole. In this case, like you want the H1 shape to go into the H1 hole, which I didn't label here, but it's like 1, 2, 3. And you want the square to go in the square and the circle to go in the circle. Well, looking at this thing, you barely have a choice, right? Maybe you could stick the circle inside of the square there, but you'd have to try pretty hard to do that. Really, you just take the shape and you put it in. That's what this is trying to communicate. Whereas in non-typed languages, it's more like you have just squares for everything. Now really you don't have any choice. You have to read the labels and say, okay, this one on the right is actually the one that's supposed to go on the left hole, and this one goes here and that goes there. So it's more cognitive work. And in super typed languages, which I think Agda qualifies as, is you can have like really specific shapes of these holes. Like your type system can express almost anything. Like there really is only going to be one thing that fits in there. But if you to go with the analogy, to stay with the analogy a little bit, if you're working on a surface where you have to carve out these holes, and the surface is too brittle, maybe you'll create a little hole. Maybe you'll like shave off a little piece here, but then the whole thing breaks, and then now you have a little crack over there, and that's not really what you want. On the other hand, if it's too elastic, you can just you can take one of these holes and just really push something in with everything you have, and it'll come out the other side, and it'll kind of work, like putting an any in a TypeScript piece of code, say. So we want the right material. There's such a thing as a good balance between convenience and correctness, in my view. And there's two ways in which you can not have the right materials. You cannot have it from two different directions. One is sometimes the cost of typing is too high. I don't know if you saw this news. It was very recent, but a big library in TypeScript in the JavaScript ecosystem is just dropping TypeScript. I don't know much about that, but I didn't actually expect this to happen. I thought, up to this point, I thought it was generally, yeah, everyone's going to keep adding types to everything. Because the cost of convenience can be high, which is why you see dynamically typed languages in which things are easy and nice to prototype in. They just keep adding type systems to their stuff. And getting the right material is hard. This is a little snippet of code from a PureScript library I'm working on. I don't know if you can read that, but it doesn't really matter. The point is this is a wall of code, and this is expressing something that is not that complicated. And here is an answer from Connor McBride, which is a really good programmer who knows a lot about types, and is what he has to say about the singletons library, which is, if you've heard of that, it's basically a mock-up of dependent types in Haskell. It's adding even more type safety than Haskell already has. And the question here was, what do we gain with singletons? And well, they're just an annoying thing that we hope we never have to look at again. But I think Agda gets really close to striking this balance. And I just have one more slide here, which is introducing the language. It's a dependently typed, purely functional language developed at Chalmers. The syntax is very similar to Haskell. There's some key differences. We'll get into that. It's based on Martin Löf type theory instead of Hindley Milner. Martin Löf is a Swedish logician on the left here. This is a fun fact that the name comes from Cornelius' song. And that's actually the icon. It took me a while to recognize that this was a chicken. It was created by Ulf Norell, also a Swede. There's a little table on the side here, which is shows how Agda is trying to uniformize. Is that a word? Make uniform. It's trying to blur the distinction between types and values. It's just you fling things around in a pretty uniform way, whereas in something like Haskell, each one is its own syntactic thing, and it's a different universe of expressing things that are really equivalent. But that's it for philosophy and motivation. I hope that you're eager to look at some Agda code now. That's what I was going for with these initial slides. So let's do it. We're going to go over a few modules that I have ready here. One going over the syntax of the language, just to show you can see what it's like to define a type, a function, etc. Then we're going to go into this idea of propositions as types. How many people in this room does propositions as type, does this mean anything to you? Raise your hand if it does. All right, a few people. Cool. I want to know if I'm speaking your language here. Then we're going to have a very small matrix library with some matrix operations. And then finally, we're going to actually jump into the Haskell FFI, which is Agda's version of an escape hatch. So let's go. This is the first module where I introduced the syntax. And let me just update my little my little phone helper here. So a few words on Agda mode. I think most Agda programmers use Emacs, and I've never used Emacs, but apparently it has a lot of this control C, control something else thing, and that's just like it's a command. What, you want to ask something? Yeah. Yes, I can. Thank you.
Can we use light level here? Light theme.
What? Oh, because it's too dark. Okay. Ooh, I actually don't even know how to change that in VS Code. Preferred light color? No. Someone suggested something. What's? Okay. Command K, Command T. Ah, okay. Whoops. All right. Nice. Oh, that looks pretty good, actually. Thanks. I guess I can increase the font on the side here also, although we're not going to see that until the end. All right. Is that better?
Yeah.
Cool. Yeah, so Agda mode. It's a bunch of commands that as you write code, they do stuff for you. These are the main ones. And I'm going to be, the very same Connor McBride has a technique where he sticks a camera on top of his keyboard so you can see which commands he's running also. And it shows up on the bottom here. If you have a keen eye, you're going to be able to see that as I run these commands. But yeah, there's loading and type checking, that's a single module, refining a whole. This is 99% of where Agda programming and testing and REPL stuff, that's, well, the equivalent to a REPL situation. That's where it happens. So, and the output shows up all here in this little tab. So let's just get started. First of all, here are some types and their values. This looks very much like gadded syntax in Haskell. If you're familiar with that, you say data, this is the name of the type, that's the type of the type. Yes, there's no kinds in Haskell. Types just have types. They're called sets, because really types are just a collection of values. Where, well, this constructor has the type 3, 2, 3, etc. And this is an example of a value of 3 and another one. Agda supports Unicode, as you can see here, with this little 2. It's very, very much not shy about that. So it's a common thing. And we're going to make lots of use of Unicode. But this is 2 different values of the type 3. That's how you define a sum type. Here's the equivalent to Haskell's either. You can see, I mean, this, if you've seen Haskell before, or PureScript or some other dialect, I would say, this looks very similar. There's a type on the left, there's a type on the right, and there's 2 ways to get an either A or a B. You can either do the left injection, which takes an element of type A and returns you an element of type either A or B, or you can do it on the right. And here's a value of either. So this is, we introduced another piece of syntax here. This is an implicit parameter. So when we call this value, when we use this value, we normally don't want to have to say what the type A is. It's just it's gonna be obvious from the context, hopefully. But sometimes, actually pretty often, we do have to give this argument. So what this is saying is that value of either has a type of either natural number or any type at all. Well, because it's a left 10, that natural number. And here is the syntax for product types. So you'll notice that there's a different keyword there, record. And well, the reason is that there is a fundamental difference between product types and sum types, co-product. They're the dual of each other, and I think it's just nicer on the eye. Personally, I like having a little section where I specify what the fields of the record are, what the product type. I mean, those 2 things are the same if you didn't know. Whenever you define a record in your favorite programming language, really you're defining a product type. And Agda makes that pretty explicit. And you can give a constructor to build one of these types up. And we see this being used here. So this is a pair where it contains one value of 3 and one value of bool. The type 6, that is. And a value of 6, you just use the constructor to build it up. Here's the definition of Haskell's tuple type, the pair of two different types. Again, it takes two types as parameters. One goes on the first field, the other goes on the second one. Pretty straightforward. This is how you construct a pair, because we gave the pair constructor a name. You'll notice that you don't need constructors to be uppercased, unlike in Haskell. Yeah, so that's pretty basic. Here's an example of how to define a function. Again, similar to Haskell. There's a function that takes two natural numbers and adds them, and a function that pattern matches on one of its arguments. So you're adding one of three values to a natural number. So if your value is 1, you add 1. If it's 2, you add 2, etc. And this still looks very similar to Haskell, I hope. And let's see some more syntactic things that are pretty cool. So Agda supports mix-fix operators. So this this function is named pretty freaky, but it makes sense when you use it. Like add this first argument to that second argument, but only if something and something else. Otherwise, pick one of them. So it takes 4 arguments, which are the four underscores here, and it returns a natural number. And you can see the body here. Let bindings, they just work like in Haskell. So you do condition 1 and condition 2. It's a Boolean operator here. And if both of them, then you sum them up. Otherwise, you pick one of them. And how do you pick them? Well, you use this function defined in a where block. And this function uses the with keyword, which is Agda's version of case. And it's actually dependent pattern matching, which means that when you pattern match on a value of this, when you pattern match on an expression inside a with, the compiler knows something about the types in the pattern match body. And I'm pretty sure we'll see examples of using with. I think it's not going to be necessary for most of the stuff we use. And in this case, this is a non-dependent pattern match. It's just if it's false, then this returns M. Otherwise, it returns N. But yeah, this is what this looks like. And there you go. This is the value of 15. Add 10 to 5, but only if true and 5 is less than 10. Otherwise, you pick one of them. This is 15. And here's add 15, which takes a function, takes a number and adds 15 to it. This is just to show the lambda syntax. The lambda is this nice Unicode lambda, like the actual Greek letter. I think it looks cool. So this is like in Haskell. This is we're saying that, well, this function has type natural to natural, and well, this value is something of type natural to natural. And what is this value? Well, it's a function that takes a natural number. You might have also have written this, like in Haskell. So, yeah, lambdas are a thing. And now let's get into propositions as types, because you need to understand this in order to do useful dependently typed programming. So we're going to import our syntax module. You'll see this open import, open in front of the import name here, which is just saying bring everything in this module to scope and treat it as like a top level variable here. You can hide stuff from modules import. So here we're importing some stuff. I try to keep it minimal. That's the kind of the stuff that we import from the standard library, but you can hide things. You can hide names. And now we're going to get into some of the actually dependently type stuff. So this type here is the equality type. And what this means is for any type set and for an X that is a member, for any type that is a member of set, and for any element of that type, give me an element of this type, and I'll give you back a set. Okay? And refl, which is the sole inhabitant of this type, has type x equals x. So what this is saying is, for a value, so the only way that you're able to pattern match on this type, or that you're able to do anything at all with it, is if you have two values that are equal. Okay? So the x here is on both sides of this constructor. See that? So it's appearing both here and here. There is a difference between a type appearing on the left side of the colon and on the right side, but I'm not going to get into it exactly. What I'm trying to show is that even though this thing takes two parameters, you can only construct a value if really they were the same thing all along. So Agda is able to just compute this on the type level. So here we have a hole, which is the first result of running load, the command, the Control-C, Control-L command in this module. And this is the hole 0. And this hole has type 11 plus 4 equals 15, the value we defined before. That's the type of this. So this is how propositions as types is caching out. The proposition that 11 plus 4 equals 15 is the type this. I didn't say it because I would just say the same thing again, but they are the same thing. Propositions are types. They just are. That's a fundamental fact in logic and computer science. And what is the inhabitant of this type? Well, it's the unique inhabitant of the type equality for these two values. And now I'm going to use a very powerful command, which is Control-C, Control-A, to automatically solve this. Agda is able to figure out that the proof of this proposition is the value of this type. That's the correspondence. Propositions are types, proofs are values or programs that show the type. A value of a type is evidence that the type is true or false. We're going to see some more stuff about this soon. If we wanted to prove that 11 plus 13 is equal to 15, that's just impossible. I hope that I don't have to convince you very hard of this. But if I put, and now I'm going to use the command to show me the context here. What I'm trying to show is that, what I'm trying to show, and this is the output that we see, that I'm trying to show that the computer number 14 is equal to the computer number 15. You can't show that, really. We'll see more examples of using the context soon enough. So you could define other relations in terms of types, like a number being less than another number, or anything really. Well, any proposition. But there's another way to think about it. If a type is true, it's inhabited. It has at least one value in it. It's a set with at least one element. If it's not inhabited, it has none. And these two fundamental truth or falsity states are represented by these two types. This one is called bottom, and this one is called top. We good? Is it?
Yeah, it's fine.
That's a scary sound. It's a fire alarm. Okay.
Because it's late alarm.
Oh, okay. That's okay. Much less scary now. Right. So these two types are uninhabited and inhabited by a single thing, respectively. Bottom is also called false for obvious reasons. It represents the fundamentally false proposition. And top is called true. Top has the single inhabitant TT, and that value is evidence that the proposition represented by the type top is true. So we can now define relation based on these types with dependent functions. So look at this. This is a function that takes two natural numbers and returns a set. It returns a type. Okay? And let's think about the logic of this. If 0 is less than or equal to n, well, if we pattern match on the first argument, we know it's true. Like 0 is less than or equal to any other natural number. So we represent this by the type top. And I had this was supposed to be a whole, but we'll fill out the other ones. Now, what about this case? What if we have the successor of some number? If you don't know the piano, I guess I should have asked this, but the piano representation of natural numbers is 0 is a natural number, and the successor of a natural number is a natural number. That's an inductive definition. And that's what we're pattern matching on here. So the successor of a natural number, or the lowest a natural number can go, is 0. So this is at least 1, this thing on the left. And 1 is not 1, or anything above 1, is not less than or equal to 0. So this is the type bot. This is what we're trying to represent. This is the relation we're defining. And the type, and what about if you have two natural numbers that are both successors of something? Well, the left one is going to be less than or equal to the right-hand side if the predecessors of both is less than or equal to the right-hand side. So this is going to be, that's a slow monitor. This is going to be this. We're just recursively calling our relation. And then we can have a little proof here that this thing works. Well, we should expect this to be true, right? 0 is less than or equal to 100. And we see what our goal is. What is the evidence that we have to provide that this is true? It's the type top, which has a single inhabitant. I wonder if we can ask Agda to just give us the type, the value of the type top. Well, of course it can. There's only one inhabitant. It knows from looking at the type that this thing is true, or it resolves it computes the type, and then it says, okay, this is what you have to provide. This is the evidence that you have to provide, and the evidence is trivial. We also have strict inequality. So here we want to say, well, 0 is not less than 0 this time. So, we'll have bot there. This is also obviously false. I mean, something that follows anything else is obviously not less than 0. But 0 is less than or equal to any successor. So this is going to be top. And then recursion for the last case also. I have my cheats here. As you might know, live coding is tough. And in fact, because I am moving a little slower than I thought, I am going to blaze through the last of the the latter part of this propositions as types module by just uncommenting the holes, and then we'll go through the code. Because I am being pressed for time here. We have quite a few things to get to. So what is this saying? A type-safe subtraction. We're saying that any m less than any n will provide an n, another natural number, only if you have a proof, or give me something of this type, that n is less than m. And here's what Agda is doing. If it sees 0 on the right-hand side, it already knows that the thing on the left is greater than or equal to it. So you can just provide the TT value. It pre-computed it. And so m minus 0 is obviously m. Now if you have m minus the successor of something, what should this be? I mean, you can't really ever give a proof that this is true. You can't ever give a proof of this part of the equation. And if you had a proof of this, you would have an inhabitant of the bottom type, which doesn't exist. So the way of expressing that is with this open and close parenthesis here. It's called the empty pattern. It's not unit like in Haskell or anything like that. And then if you have a successor of something minus a successor of something else, and a proof that the left-hand side is greater than the right-hand side, well, you just recursively call the subtraction function, removing on the predecessors of these numbers. So here we can test that our subtraction thing is correct, our subtraction function. And you guessed it, Agda is going to compute this automatically. It just knows by looking at the type that the two sides of the equation on it are the same. And that's basically the idea of propositions as types. I could do more advanced proofs, but I want to get to the programming with dependent types part of this. So we're going to go slightly faster here. This is a prototypical example of dependent types. It's a vector where you know the length of the vector at compile time. Doesn't actually mean you know it in advance. Obviously, you get user input and all that. But the point is that it's part of the type. Vectors in Haskell or in any language, well, most languages, usually the vector just contains some other type. They don't have a length associated to them in the type itself. Not so for this case. You have the empty vector. How is this type defined? You have the empty vector, which has length 0. And you have the cons vector, which has this constructor takes an element, takes another vector, and gives you back a vector with that many elements of that type plus 1. You're just going to stick the thing. You're going to stick the first element you received in front of it. And here is the, now I see that things are not, I can toggle word wrap, I think. Yeah. So that we don't miss anything. Here's the take function. I'm going to rely on the cheats. Whoops. Instead of filling this out. So the take function is, give me a number, give me a vector, I'll give you that many elements taken from the front of the vector. But in this case, you have to give me a proof that the number you're giving me is less than the length of the vector, right? Give me a number a, give me a proof that a is less than the length, and then I'll give you a vector, a long, from the first vector. And you might have seen this in Haskell. This is not, there's nothing fancy going on here. taking 0 gives you back the empty vector, taking the successor of something. You take one element, you move to the back of the vector. Here's concatenation of two vectors. Let's just rely on the cheats. So if you have an empty vector, really you're concatenating an empty vector with the second one, so just return the second one. Whereas if you have something on the first vector, traverse it, put it in front of the result of concatenating the rest. Here's getting an element in a vector. Again, you have the length of the vector, and you have a proof that, maybe the word wrap was a bit of a bad idea, but you get the idea here. You have a proof that the index you're looking up in is less than the length. You'll get that you get something of that element back. Very similar to take an idea. Constructing a singleton. We're making good use of the singleton of the mix-fix operators here. Give me an element, I'll return a vector of length 1 with that element in it. Here's a little proof that our right index works. Auto-solve, baby. Agda just knows. You say that the type of this thing is looking up the index 2 in the vector v, which you've bound here. Yeah, there's let bindings in types, which is extremely awesome in my opinion. That is equal to 6. Yes, it is, of course. And some usual high order functions. I mean, map. Who doesn't love map? Just apply a function to a vector and traverse the rest of the vector, applying the function as you go. Here's point-wise application. So you have a function, you have a vector of length n that contains functions from a to b. And then you give a vector of a's, and you expect to get a vector of b's back. This is not a super usual higher-order function. It should remind you of applicative functors, but we are going to use it soon enough. That's why I'm including it here. We're also going to use replicate, which is give me an element, and I'll give you a vector of length n, whatever n is. N is being given as an implicit argument here. But when n is 0, again, same idea. When n is 0, return the empty vector. And when n is successor of something, put it on in front of a replication, calling the same function on the tail. Here's transposition, which is if you have a vector of vectors, you should basically exchange the rows with the columns, which is using some clever application of pointwise here, which is why we needed it. Yeah, I won't have time to explain transpose, unfortunately. But it's cool. If you can stare at this code and verify why it works. Or you can just write a proof that it works. For any type A, and for any 1, 2, 3 elements of A, transposing this matrix should give you this matrix, right? 1, 1, 1, 2, 2, 2, 3, 3, 3, 1, 1, 1, 2, 2, 2, 3, 3, 3. Guess how we solve this? It's done. That's for any type and any 3 inhabitants of this type. I think this is our final higher order function, which is zip width. You might know zip. If you don't know zip width, it takes 2 vectors, a function that takes 2 arguments, and applies that function to the 2 vectors as it goes. That's why it's a zip. Zip is like a zips of a pen, so zzz, and then you get a single thing out of 2 strands. Let's look at a few more dependent types. Now, this is when it gets real. This is This is called the sigma type. That's that word. That's that letter here. Give me something of type A, and a function from an element of A to a set, and I'll give you back a set. So the fields of this are, the first field has type A, the second field has that function applied to the first field, to the element of the first field, whatever it is. And to show this dependent the reason the sigma type is called the dependent product, and the reason is because it's a pair. It always has two values, projection 1 and projection 2, except that the type of the second pair, of the second element, depends on the type, on the value of the first one. And here's an example of this. So there's a function nat if false, list of top if true. Right? It just takes a bool, returns a set, pattern matches on the bool. If it's false, returns the type of natural numbers. If it's true, returns a vec for any natural number. It returns a vec of tops. And here is a value of a dependent product that uses this function. So this is a product of bools, and this function is the second parameter we give. So this function is, well, what should the type of the second value be? The first value is false, so it should be a natural number, which is why this compiles. The second example is, well, this is true. So the type of the second thing is this list of tops, 3 tops. I don't know why you would use that, but it's just to illustrate that you can have a product type that it varies depending on values. We can have expression and type signatures. Now I have to really go fast here, but this gets crazy. Like you can do a lot with it. Here's the type of set of natural numbers that are greater than 5. You just define it as a dependent product where the second element is a proof on the first value. And you can construct a proof that the value 7 is greater than 5. The proof of it is going to be TT, because it's computed in the type. But you can't produce a value of greater than 5 with the first element being 3. The type of this hole is going to be bottom. It's impossible to produce a value of bottom. You can parameterize this over the natural numbers, so you have greater than n. Here's the value 9 is greater than is of type greater than 7. Of course it is. All right, you with me? Still have quite a bit to get through. I'm going to have to blaze through this last part because I want you to see this cash out in a program, a simple program, but still. Let's get to this module, where we write a little matrix library. We're using the natural numbers. We're using our previously defined stuff. We're going to define a record here, which is num, takes a set, returns a set, has a bunch of fields, which are functions on this set. Some of them are values, but this is functional programming, so functions are just values. And what this is Agda's answer to type classes in Haskell. If you didn't know, when you're a type class in Haskell, it just reduces to a dictionary at runtime. For this type, the implementation of this function is this. For that type, the implementation of this function is that. Agda just makes that a lot more explicit. This is some syntax to bring the members of this record into scope for the rest of the module. And here's how we declare instances. They are just values of this record. You define what you define all the fields of the record for this set, natural numbers, and for this set, the real numbers. This syntax for creating the record here is called co-patterns, which I think is fun. It's basically you give the type of the record and you say what this function applied to this record is. The reason it's called co-patterns is because Patterns, when you match on a pattern, you're deconstructing it to say, for this branch, do this. Whereas for a copattern, you're saying, from every possible angle, here's how you construct this. So you have to yeah, I hope it's a little hard to explain. But it's basically how to construct something based on the fields it has versus how to deconstruct something based on what it could be. It's a dual, co-pattern, category theory, haha, yeah. And this is how you say that this thing is an instance argument. It can be used as an instance argument. You say, you just put the keyword instance in front of it. So let's go over the matrix type and the functions on it. It's basically a new type over a vector of vectors. You have the number of rows and number of columns and any type for it. And you can add two matrices together as long as they have the same dimensions. This is what this function is defining. Again, mix-fix operators. So the way you sum two matrices is, well, you zip with the first vector, with the first layer of vectors, zip with the second one, sum whatever you find on the way. That's what this little nested zip with is doing, applying it to the two matrices. I thought I toggled the word wrap. Yeah, here we go. So give me a matrix of A, another matrix of A. I'll give you another matrix of A with the same dimensions. Multiplying matrices is more interesting. Now you're saying, well, a matrix with dimensions R and C and a matrix of dimensions C and P can be multiplied to produce a matrix of R and P dimensions. Very natural to express. Won't really go over the implementation details here, but you can look at the recording again, stare at the code, make sure it works. Oh, I already told you to stare at this code actually, because it's using the transpose we defined on vectors. So you're going to have to stare at two layers of code actually. Here's a few other functions that are just nice to have. Give me a vector, and I'll construct a column matrix out of it, which is a matrix with a single column. So that has n rows, that being the length of the vector, and one column. And a vector to a row matrix has a single row and n columns. And this is just a synonym for transposing, but if you've seen matrices written in mathematical notation, they have this to the power of t thing, which is neat. Yeah, you've seen these infix declarations peppered throughout. That's just saying whether an operator associates to the left or the right. In this case, it's a single argument, so it doesn't really make sense. And the priority and how tightly it should associate. So that's a little matrix library. We can add and multiply, transform vectors into matrices. Simple stuff. And we want to get the pseudo-inverse of a matrix now. That's a tricky operation. If you've ever tried inverting matrices before, you'll know that it's not a trivial algorithm. Like loop decomposition and verifying that a matrix is non-singular, that stuff is hard. So going back to the Lindy effect thing, Agda has a way of relying on that part of how much you can trust code, like whether you care about the code being correct. You can rely on code that has just been out there for a long time and kind of trust that it's correct by using the FFI. Agda is compiled down to Haskell. That's how it ultimately runs and creates stuff on the screen for us to use. And it has an FFI, so you can call Haskell code from Agda. You can also call Agda code from Haskell, which is interesting. And Well, there's not much to say about this one, except you might see this. You're gonna look at this trust me being used, and this is exactly the point where it's like, yeah, forget about all the type safety stuff. Just trust me, this thing works. That's the actual name of the library, by the way. It's not. It's the actual name of the package. It's called Trust Me, and there's a proof in there that is anything is equal to anything else. Just trust me on this. It's correct. So this is how it works. Oh, gotta toggle word wrap again. There's, I think, 3 types of pragma for using the FFI. So this is telling the compiler, when you get down to compiling this part of the code, insert this Haskell code in there. Just import HS matrix. And what is that? Well, we'll see. Here's another pragma, the compile pragma. When you see this postulate, and a postulate in logic is something that we just state, this is true. Like let's pose this proposition. They kind of take, I guess they fight over the spot of things that are just true because they are with axioms. I think there are differences between postulates and axioms. I'm not actually sure, but that's how you just carve something out of thin air from Agda, and that's how you use that's what you tell the FFI. Whenever you see this postulate that takes a list of lists of real numbers and returns a list of real numbers, tell it to be invert matrix as list. This is Haskell code. This is the thing that it's going to cache out to. Instead of trying to compile this thing whenever you see it, just make it equal to this Haskell code. There's some conversion code here for turning lists into vectors and vectors into lists. I'm going to have to skip all of that, except for this part here, the trust me proof. Like, don't worry about it. Just, this is gonna work. Trust me. I just love the name. So we use from list of lists for calling the postulate. This is the inversion operator to the power of -1. First, you turn your matrix into list using our conversion function. Then you inverse it. You inverse it by calling the postulate, and then you convert the thing you got back with passing trust me's again to make sure that the dimensions match. So that's why you have give me a square matrix for any n. You have a matrix of dimensions n to n and n. I'll give you back n and n. So this is now an Agda function. Like this, it works on the Agda level. Proofs are going to be, or terms are going to be tested against the proofs that your n is, that your matrix is square and that the input is the same as the output, etc. And here's some code for displaying matrices. Again, we use the standard library for that. Yeah, it's just, there's not much to it. Just recurse over a vector and intersperse the thing with commas. Should look very similar to Haskell to you. And yeah, to show a matrix, you just use showvec. So the last module that we're going to look at is the main module. Yay, we're not just heating up the processor, we're actually running something. We do some imports here. Agda's relationship with I/O is, as you would expect, complicated. There's some syntactical, not just syntactical, there's some noise in this, like this level 0 thing, the fact that we have to run an I/O call, despite the fact that we're already running an I/O, like what's going on? Don't worry about it too much. It's really, you should sort of not look at this IO.run or the level, the level calls. This is just an I/O call to print a matrix. Give me a matrix, I'll give you an I/O operation that returns top. And here's our main function. let our matrix M be this matrix 2, 6, 3, 4. Let M_inv be the inverse of it. And then we should see, well, what we should see here is, first we're going to print our matrix, then we're going to print its inverse, and then we're going to print the matrix times its inverse, and this should give us back the identity matrix. If I'm lucky, of course. So I have this little build command here. It's created by this Nix shell, where it's going to compile our code. It linked it, and we can just run this code, and there it is. Our matrix M is 2, 6, 3, 4. Its inverse is minus 0.4, etc. And it times its inverse is, whoops. Oh, Jesus. Was that right? Yeah, so 1, and then a 0.4 here, and then something to 10 to the power of minus 16, and then something to the power of minus 16, and then 1. So this is really minus some floating point error. This is 1, 0, 0, 1. That's the identity matrix. And yeah, this is, that's essentially the content. I'll just add a little appendix here, which is showing you what that Haskell module looks like. And here it is. Ooh, it's not actually using singletons. That's for a future talk. But this is using an external library. This Haskell file relies on an external library that is being fetched from Hackage. It's called hmatrix, and that implements the pseudo-inverse algorithm. This is the Lindy part of our code. That code is out there. It's tested. It has been running for a long time. It relies on code that is even more well-tested, like LAPACK and BLAS algorithms. And this little module here serves between our world of trusting the Lindy code that's just been out there for a long time, and trusting the theorem-laden, extremely type-safe world of Agda. And the ultimate point, I guess, the thing I wanted to leave you with here, is that the more convenient it is for expressing correctness, like a lot of the stuff that you saw in those types are pretty natural, like 15 is equal to 11 plus 4. You know, that's, anyone can read that code and just understand it. The more convenient it is expressing the correctness of something, I think the more obsolete the trade-off between convenience and correctness is. Like, the less effort you have to spend translating your intention into something that is verifiably correct by a computer, the more you don't have to worry about, well, how many layers of tests and how much type foo do I have to do to make sure that this thing is correct. And I think Agda has a major role in this, because I think it's a quite beautiful language that makes it natural, and I'm using that word carefully here, to express what we actually mean when we write code. And I hope I've been able to convince you of that, or at least make it sound plausible to you. And that's it, an intro to Agda. Thanks again.
Thank you very much, André.
Thanks, Magnus.
I didn't follow everything.
Oh,
Even though I tried, I've seen this twice now. Yeah. Do we have any questions? Anyone?
Yep, you have a question there.
We'll send them a mic.
Yeah.
Can you show us what the type errors look like if you add an element to the matrix in the wrong place?
Yeah, I can do that. I just messed up my mic here. Yes, I can show you. You mean in the proof that of the transpose? Is that what you were talking about? Or if you just try to give... Yeah? What about it?
Yeah. What does the type error look like
If I just add, like, if I...
one element to one of the rows?
Oh, if I... Oh, right, yeah. That's a good question.
I wanted to know what it looks like if you add an element here, yes.
Yes. So what do type errors look like? So here we added a matrix that is just not well formed. It has two columns in one of its rows, and then it has 3 columns in the other one. So if we try to load this module, it says, yeah, I guess it's a little bit hard to read unless you already know what you're looking for. But essentially, it's telling you the truth. Like, the successor of something is not equal to 0. It's trying to, when it's constructing this value, it's trying to match, when it gets to this point in the pattern matching of the first vector, it's going to try to make sure that both sides of its matching are 0. And one of them is going to be suck. And suck of anything is not 0. Yeah, if maybe a better type error would appear if you do this, because, whoops. So this is a matrix that is well formed, but it's not square. So now this is a much better error. Like, 3 is not equal to 2. When checking that the expression matrix float is, if I had imported these things properly, it would look a little better. But 3 is not equal to 2 because you have 2 rows but 3 columns. So the matrix is not square. You can't invert it.
Thank you. Any
No.
more questions? No, everyone understood everything.
Yeah.
Yeah.
You were the only one.
Yeah. Sorry.
Yeah. Oh, we have a question
Yeah.
there.
Shoot. You get a mic.
Yeah. Thank you very much for the presentation. It was very interesting to follow. The question is about, maybe sound a little weird, but the application of this type of programming. So as far, yeah, it's like like where practically there is a demand to use these techniques.
Yeah, that's a great question. And using Agda specifically, I know of at least one company that has hired for it, which is IOHK. They've rebranded to IOG now. And they're doing blockchain stuff, and they're doing protocols between blockchains. So it really, really matters that the code they write is correct, and they use Agda to prove theorems there. But I know of programs developed using Agda, like a verified C compiler. Pretty sure it was developed using it, and that is used. I think it's called CompCert, and I hear it's used in like some serious applications like aviation software and that kind of thing. It really can't go wrong, otherwise people die. Yeah, I'm not. Don't quote me on that second one, but I'm 90% sure that's an Agda thing. Yeah.
Okay. I have one question. How come you came in contact with Agda?
Yeah. The way I came in contact with it was I was into Haskell, and I was doing my master's degree in complex adaptive systems, which is this half physics, half computer science thing. But I would say it's a bit out there, but I think the fundamental question is, how are things the same? Like, what is the fundamental structure of these things? So I wanted to unite what I saw of that question in Haskell. Like, Haskell is, type classes and uniform behavior across different types and everything. That's made me look for something more advanced in that space, and eventually that led me to dependent types and the master's was in Chalmers, which is where Agda is developed. So yeah, it was from Haskell to category theory to dependent types to joining that up with complex systems. And Agda was just a natural choice in Chalmers.
Okay, thank you.
Yeah.
Well, any more questions? No. Thank you very much, André.
Yeah. Thank you.
We'll do like a 5-minute pause when we swap the presenters. So in the live stream, we'll be back in 5 minutes, and here, like, you can run for the bathroom and take some stuff. Get some more pizza.
Yes.
You have to eat it up. They don't want to carry it out. They want you to carry it out in your stomach. Yes, hello and welcome back, everyone. And to in the live stream, welcome back. Now we're going to do our second presentation, Schema Management with Scalameta by Lars. Welcome, Lars, and thank you very much for coming here.
Thank you.
Yeah.
Thank you. Hi, everyone. I'm Lars. You heard I run a small company named Kling. We do data engineering, and I was going to, as Magnus said, I was going to hold this presentation like three and a half years ago. I was going to hold it at this meetup, and then at the Data Innovation Summit back in 2020. What happened then was the pandemic, and the Data Innovation Summit went online instead, and I held another presentation because I got so upset with the poor handling of data and data management during the pandemic. In fact, it was so poor that it killed people. Not in Sweden, but in Britain, it actually killed people by mismanagement of data. So that was the topic that I chose instead. And this presentation has been brewing for about 3 years, and is now finally going live after some laying still. What got me into data is a couple of events during my career. The first one was when I left academia to join Google, and I didn't work with data at Google at the time. But I learned 2 things at Google, or I learned many things, but most importantly 2. One was productivity, and I worked in productivity engineering, and I realized how much you can achieve if you run in circles around your competitors. And Google had the absolute best productivity tooling and processes at the time, and still have. So that was a great education. And the other thing that I learned was how much value you can get out of your data. This was back in 2007. Google was the only company at the time doing what later became known as big data. So that's how I steered my career. After a few years, I realized that Spotify were doing interesting things in the area, and that's how that's where I learned the craft of data engineering. Built out one generation of Spotify's data platform, the one that sort of managed to democratize the use of data within the company. I've continued as an independent consultant for a while, and with a bunch of companies, and nowadays I run this data engineering startup. I'll describe a bit later what we do. But first I'd like to get to know you as well. So I will speak about some of the things we do with Scala. And I wonder how many people use Scala here or know Scala? Okay, half of you. Some of the examples might be difficult to understand if you don't know the syntax, but I promise you it will be less difficult to understand than the previous presentation and understanding what Agda is up to. The second question, how many people here dabble with data, like in data engineering, data science, analytics, and so forth? Okay, very few. Okay. Then I will keep those things at a fairly high level, as much as I can. And I'd like to start at that high level to explain what we do and why, and then in that context I will take you all the way down to very gory technical details, so there will be a little bit of for everyone. But I want to explain the context that we do, that we operate in to explain some of the choices that we've made. All of the things that we humans do, the value creation that humans do, go through sort of phases where we start with doing things in a very manual level, cook over an open fire or transport things with a cart and horse and so forth. And then we get tools that we can hold in our hands and steer like a car. Or a stove or a chainsaw, and we become more powerful, but we still steer it with our hands. And from there it goes on to an industrial level where we as humans don't really participate as much. We just control the process and change the process and work with the process, but the process itself is mostly automated. And we have gone through these stages with the software engineering and various other technologies and with data. So the manual of data is like pocket calculators or Excel, and most companies are here in the sort of the database and data warehouse age, of data, whereas a tiny fraction of companies, and Google was the first one to break through this barrier, have gone into an industrial age of data, where they work with the processes instead. This is Spotify's flow of data from 10 years ago. And in most companies, the flow of data like fits here. So these are orders of magnitude bigger. The difference between working with as a craft versus as an industry, as I said, is that humans in the artisanal way of working, humans control the processes. And the components that you use are sort of convenient and easy to use, easy to hold. Like whereas an industrial robot, for example, is very difficult for a human to steer. It's just not made for that. And likewise, it's likewise the case with our software engineering tools and our data tools and so forth. So what happened in the sort of data evolution here is that the jump here from the artisanal stage where the data warehouse and sort of semi-automatic processes was the state of the art to this stage it was enabled by the most successful cargo culting ever, which is Hadoop. When Doug Cutting and another person whose name I've forgotten looked at what Google did and did an open source implementation doing exactly the same thing. And that spread among the Silicon Valley companies and outside of Silicon Valley after a while as well. And because of the limitations of Hadoop, people were forced to work in a different way. And that pushed some of the companies into these processes instead of the manual steering. Now, this got very hyped and really cool about 10 years ago, and all of the big companies wanted to do that as well. So if we just install a Hadoop cluster or a Spark cluster, everything will be fine, and we will get magic, and we pour all of our data in a data lake, and great things will happen. That didn't turn out so well. Most of them completely failed. There are some spectacular failures here in Sweden as well, when tons and tons of money were burned. And the conclusion was that, no, we can't do this. We go back to the sort of the old ways of working and get better data warehouses. We buy Snowflake instead, or some of the newer tools that are still sort of the same as before, but a little better. We've seen this pattern before. Back in the 90s, building programs became really, really popular. And there was a huge demand, but things like C++ and Smalltalk and Java and all of the other sort of third generation languages were sort of quite difficult to use. You needed a software engineering education. So people came up with simpler ways of building programs, right? Graphical ways, UML, you can drag and drop things, and programming should be for everyone. These are completely extinct today. There's not a single significant program written in 4GL languages. What instead happened was that we educated people. And now software programming is the most common profession in Stockholm. So what has happened now is that we have entered the 4GL stage of data engineering, basically, with tons and tons of tools that pop up and enable everybody to use graphical tools and low-code tools and no-code tools to do data engineering. And in fact, one of these is from the 90s, a 4GL tool, and the other one is Apache NiFi. They sort of look almost the same still today. Now, I may sound like I'm mocking them. I'm not. These serve a purpose, right? Because we're not here yet. We don't have the competence. So these have a value for a period of time, but we will eventually move away from them. So, what does it matter to do things industrially? It's not. I mean, there's no value in having an automated process versus a manual process that has to be translated into some kind of business value in order to be valuable. I call these sort of the platforms that we work with data factories, because they are similar to manufacturing factories. And if you look at a real factory, you can say that every time you move an industrial robot moves, some kind of value has to be generated, right? as a proxy, but because otherwise it wouldn't move, right? It's maybe drilling one screw or one hole or one screw doesn't amount to value, but the value that spits out of the factory is in some way proportional to the amount of things that happen in the factory, right? So you can say that if someone has a factory and 1,000 things happen per day, and another company has a factory where 1 million things happen per day, that million thing probably produces more value. And if you translate that to working with data, what we do in these factories is usually we work in batch processes, and the batch processes produce data sets. Some of these data sets are intermediate, but some have sort of an end value. This could be showing on a graph how many users we have, or the trends from yesterday, or recounting new recommendations for all our users, or calculating a new index for fraud detection or whatever. So if we count the number of data sets, we get some kind of hunch of where companies are in terms of maturity. And if you go to the traditional enterprises, the banks and the insurance companies and retail and so forth, they usually have these like BI teams with from 10 to 100 people. And from talking to lots of these companies, I deduce that they usually produce about on the orders of hundreds or maybe in the low thousands of data sets per day for the really big banks. When I started at Spotify 10 years ago now, we were producing somewhere around 20,000 per day. In 2017, they came public with some figures, and you could deduce that they were now at the order of hundreds of thousands per day, and there are probably, if you extrapolate, in the millions now. 2016, Google published that they were producing 1.6 billion data sets per day. And if you start thinking, well, okay, why would you produce so many data sets? How many relevant things do we have? We have the users, we have the sales report, you can probably come up with a few hundreds. Clearly, they are soon doing something radically different. The radically different is that they have moved away from the sort of the traditional value of data, which is analytics, reports, understanding of users, and so forth, out into the land of where data plays a much more significant role in the product. They sort of shape the product, they shape the logic, and all of the sort of modern AI and machine learning are out here on the fat tail. And the volume of this fat tail is large. So if you can push the cost of working with data down, you can get out here and you can have disruptive value. So what we do is to run these factories as a service. That's sort of our business model. And we don't do with what you today see as the modern data trends with the data constructs and the modern data stack and so forth. We're completely doing sort of old school big data. I will not go into details about what we're doing because this is not a sales presentation. We have a very simple marketing strategy. We share information freely that we believe will be useful. So I'm here to share some of the technical details with you of how we work. And I will say many times, we do X and we do Y. I want you to interpret this not as we do all of these fantastic things, therefore you should buy our product, but we do all of these things, and maybe some of these are useful for you. Maybe you can learn from them as well. There are a number of things that differ between success and failure here when working with data factories. Some of these fall into the organizational realm, how you form teams, how you collaborate between teams. The big revolution of big data was actually not technology. It was a new way of collaborating between the teams, where the data lake is the central thing, where you pour all the data and you make it accessible and to everyone and easy to innovate and so forth. If you read this book, it sort of describes the way that modern IT companies, the successful modern IT companies, organize most of them. The other factors here that I mentioned are ways to work with technology. and it can be summed up as modern software engineering processes. This is another epic book that sort of sums up these practices and processes as well. Building on existing, well-known, well-established software engineering processes that we know are efficient is crucial to success with data factories. But it's not so common when working with data. It might, if you don't work with data, but in regular software engineering, it might be obvious to you. It's not obvious in the data realm. So I've been talking a lot about factories. What are they? They are essentially taking the old traditional way of working with data in databases where the sort of the entities, the records are mutable, which is in a way an object-oriented way of working with data. You have these tables with records and you mutate them, change the state and so forth. Taking that and going to a functional paradigm where you say that we have raw data here that we either take facts as events or in some cases dumps of the databases out there. We store them essentially forever. I promised to go into privacy as well, and store forever doesn't go so well with privacy, but bear with me for a while. We have a simplified model for now. We store these things forever in raw form without any processing whatsoever. And then we refine the data and create valuable things out here to feed our services and to feed our analytics by step transforming these things. So we do this at an architectural level, right? But this is essentially functional programming, turn into architecture. And this is what Hadoop forced us to do. We didn't understand this when it happened. But because it couldn't do indexing, it couldn't do transactions, so you couldn't change things, so we were forced to do like sort of MapReduce steps and implement the business logic as functional transformation. And therefore, we were, since we couldn't do transactions or anything, we were forced to make these data sets immutable. And it turned out when we made them immutable, anybody could read them without disrupting our own service. Whereas if you go and bang here, you disrupt the operations of the service and you don't know how it changes and so forth. But since these are immutable, anybody could use them. And I discovered at some point that a data set that we produced were used by 200 different use cases downstream without us knowing it. So that's a great example of sort of minimizing friction to creating business value, because each of those 200 created some business value for the company, and without synchronization between the teams, which is usually the bottleneck. Schema management. All of this data has some kind of schema. The schema defines the structure of the data. And in some cases, in relational databases, these are very hardwired. You explicitly have a schema for a table, and the relations between them are stored in the database as well. Whereas we don't work so much with databases, we work with file storage, and then the relations between the data sets are sort of implicit in code rather than expressed in the storage. Somehow we need to define these schemas, and there are a bunch of different strategies. One of the popular ones is to use Avro definitions. Avro is a serialization format suitable for data storage. If you've used, some of you might have used protobufs or Thrift or whatever, it's similar, except that with Avro, the schema is actually stored with the data, which turns out to be a lot more convenient when working with data storage. I've seen all of these in some form or another. So you can choose either to have sort of specific formats or have code as the way to define your schemas. We use Avro as our serialization format. For various reasons. It has a couple of different variants. You can either store it binary, in which case it's very compact, or store it more verbose as JSON. Either way, you need to have some kind of code to sort of serialize and deserialize again. And when you store it in files, the schema is attached to the binary record, so that tools that read data can also find the schema and understand the data. There are two main strategies for sort of keeping schemas in consistency. One is called schema on write, in which case there's when data is produced and put in storage, there is a clear definition on what the schema of that particular data should be like. If you're used to relational databases, this is what all relational databases use. In the case of relational databases, there's a check as well. So if you try to write something invalid, it will technically fail, and you will get an exception. You can do schema on write, but without technical checks, and then it's sort of more of a social convention that if you wrote the wrong thing, you're a bad person. Now we lost the display here. I don't know why, to be honest. It still says. Things were going so fine.
Yes, you were doing really fine. You try lock on accepting. Norwegian reset.
Now it's just dark. Den där donglan är inte lika pålitliga som den där normalt sett. Det är dongen som gäller. Ja, just det. Men jag vet att de där inte, eller om det är datorn och de där som inte är riktigt pålitliga.
Har du testat den där? Om du tar med skrivbordet och högerklickar.
Nej, det här är en Linux-burk.
Alltså, förlåt.
Så det är... Så, bra. There we go. Thank you for your patience. So schema on write is a sort of represents a philosophy of strictly checking what data ends up in the storage. The opposite is schema on read, where we might store a little bit of everything, but then as we use it, there is of course an expectation of what we are supposed to find there. And in that case, we sort of check when we read things that all of the fields that we read out are present, or otherwise we will get some kind of exception or problem because we don't have the data that we need. There is an interesting property here, is that if we change the schema that we write down with schema on read, when we sort of join things or copy things, the new fields will sort of flow along, right? Whereas in a schema on write situation, which is typical for data warehouse environment, we need to change the schema in all of the tables where we propagate the data. And the strict and loose typing is similar, but not the same, as the philosophies of static and dynamic typing, like in languages. Because in static typing, these are the fields that are supposed to be in the record or in the class. Whereas with dynamic typing, we can accept a little bit of everything, and we don't. If there are some extra, we don't care. They just float along. We, in order to sort of read and write code, we sometimes decide to generate code, and then if these two go better together and these two go better together, but we can also sort of cross-pollinate a little bit and sometimes do. The effects that fields that we add out here in the source propagate through the systems, through the pipelines, through the steps of batch computations out here to where we need them is very handy for analytics purposes. Because then you can ask the people in the that handle the mobile client to say, oh, can't you just add a field for like screen resolution or whatever? That would be really useful to know. And then suddenly it pops up here without having to synchronize with all of the teams in between. Remember, synchronizing between teams is usually the bottleneck. But the drawback of this is that if you make a little typo out here somewhere and you get it wrong, then much later you notice the problems, which if you don't feed analytics but feed real world applications, this might not be the desirable trade-off. This is one of the oldest slides that I have. It's like 10 years old or something, but it sort of still holds. Since I made this slide, this has shrunk, and schema on read has become a lot more popular in data pipeline applications. There's also questions of compatibility. If you mostly work with APIs and microservices, you also have schemas there, but and then if you upgrade, you need to think about the compatibility if you have an old client and a new server, or the other way around, right? That compatibility problem becomes much more significant if you work with data, because with microservices, once everybody has upgraded, you're all on the new version and you can forget about the old. Whereas if you store data, you can store for years and you have all of these old schema versions hanging around. So you have to have some kind of strategy. And when changes cannot be made either forward or backwards compatible, you have to have a strategy for sort of incompatible changes. And there are a couple of different, what we usually do with our clients is to just recompute everything, which works because our clients don't have huge amounts of data. If you have sort of web scale data, this is not so convenient, so you'd pick one of the other strategies. This is also a very, very old slide. This was made back in the days when all of the big data innovation happened on the JVM. Nowadays, Python is completely dominating, or mostly dominating at least. The reason that Scala bubbled up in this world is that it connects sort of to good properties from two worlds. One is the JVM world where you have the static typing and you have good operations tooling and so forth. But if you put data scientists and say you now need to go and do your prototyping in Java, they will go find another job because of all of the boilerplate and so forth involved. So we found that sort of Scala was a common ground where these two kinds of philosophies could meet and actively work well together. And that's why some of the popular big data tools were made in Scala. So zooming in now onto Scalameta, which is a tool that we use for parsing Scala source code. Scalameta is a parsing tool that parses code, and then you get a representation of the code that you can manipulate and either write down again or do something completely different. There are a couple of levels when you're parsing code. One is the tokenization or the lexing, where you take this and you split it into words, basically. And then from those words, a syntax tree, an abstract syntax tree is formed that represents the code, but doesn't understand which types are actually which. It just knows them sort of by name. And then there's a step of semantic analysis where these names are resolved to actual types. Right? Scala, if you have a C preprocessor, it works at this level. Scalameta somehow works at all three of them, but mostly on this level, and this is where we are going to be working today. There are a couple of use cases of Scalameta. One is formatting, which is where it needs all of the little nitty-gritty tokens as well. There's a code formatting tool called Scala Format. There is a tool called Scala Fix for static analysis of code. So it can give you warnings, tell you if you have unsecured code or whatever. Scalameta is nowadays also used as the macro implementation in Scala 3, which is called online code generation. It's dynamically generating code while you are compiling. What we use it for, which we'll see, is offline code generation. So during the build process, we read the source trees and generate code. It says code transformation here. This is a quite cool application of meta programming or of Scala Meta. This example is from a file in the Schema library. It's a data processing library from Spotify that you can use if you're upgrading from 0.7 to 0.8. Then this is a transformation rule. So if you apply this to your source code with Scala Fix, it will change all of these calls to this function to another name instead. So that's a very sort of automated approach of upgrading libraries that I haven't seen in any other language. So what you get when you ask Scalameta to parse the code is a syntax tree. And this code here, which we will see examples of later, translates into sort of this tree. This is not Scala syntax. This is what you get if you say please print the tree on the screen. And you can see sort of the structures here are represented by structures here. And you can sort of deduce that yes, we can probably go around and program our way and navigate this tree. It can be a little bit difficult to realize, the match between these when you're programming. So there are a couple of cool tools in Scala Meta. One is called quasi-quotes, which basically, instead of saying, here, I have a piece of Scala here, can you please parse it and give me the tree? You apply this little quote here. And this is a macro that actually also type checks, right? So it reads this and it makes it the right type. So you get a compile error here if you have a syntax problem inside here, which is a bit odd but cool. That confused me when I first used it. You can use quasi-quotes the other way around, so you can use them similar to the way that you used regex matching in Scala. I don't have an example of the regexes, but when you do regex matching in Scala, you have this matching case statement, and then you have this regex, and you can have some groups here, and you can pick out the data from those groups. So you have the same type of matching and says, hey, does my source code match this pattern or this source code pattern? If then, yes, please give me those pieces like the A here and the B here and so forth, and give them to me as variables with the right type, of course, so that I can work with them. So schema definitions, back again. What we have decided to use is to use Scala case classes as our schema. So for those not familiar with Scala, a case class is a dumb record in a way. I think they're called records in Java. It's similar to data classes in Python. So they are used for sort of transparent, simple records of data with a number of fields and so forth. You get a lot of syntactic convenience, so they are very attractive to use in Scala. And then we use, as I said before, Avro for our sort of serialization format. From these case classes, we generate a whole bunch of different things to help us with the management of schema in different parts of our ecosystem. And when I did this presentation 3 years ago, we only had this one, so it has now grown a bit. And I will briefly go through all of these to give you examples here. So one is the Avro codec, and you'd think that Avro, being a very popular format, you could just take a case class as record and say to Scala, please save it as Avro. And that we tried that for a while, but the libraries are not really good enough so they mishandle some cases. These Java libraries are better. So what we do is we generate Avro definitions, which look like this, from our case class definitions, and then we ask the Avro tooling to generate the Java serialization code. And then we don't want to be in Java land because Scala is a significantly much better language for data processing. So we generate converters that in the IO routine almost immediately convert Java to Scala. You might think, oh, how about performance? We don't care. There are three dimensions of performance that are relevant. The one here is that you might think about is runtime performance. That's mostly irrelevant to us because most of our clients have small amounts of data. The performance that we care about instead is developer performance, the ability to quickly iterate through new things, and that's much more important. And the other one is test case performance, so if the tests run quickly so that we can iterate quickly. So the evolution of code is much more important to us than the actual data execution. And this is an example of code where we generate these converters. And now you see the quasi-quotes shine here, because instead of building this huge construct tree, we can sort of program Scala within a string and inject all of these different sort of template variables to form Scala code. And if we get this wrong, we get a compile time error. In some cases, we receive data CSV, and there's a fairly good Scala library called Kantan CSV. It needs some help a bit here and there to sort of interpret headers where it sometimes gets a bit confused. So we generate some of the helpers and codecs that are sort of case class specific as well. When we test code, we usually run data processing jobs and say, here's the input data, run the job. Here's the output data. Compare the output data either with a known fact, what it should be. Sort of if you produce 10 records, here are the 10 records that you should see, or we just look at bits and pieces. And one of the problems we had before is that if any of these records contained floating points, you would have an exact floating point match if you just compared one record to another. That leads to very spurious errors when you differ in the decimals. So we use type classes called record equality here to say that, okay, two records are defined as equal. If they all match, but for the doubles, you can allow a little bit of leeway here so that you don't get confused. And for those not familiar with type classes is basically a way of saying, hey, to the compiler, hey, if you have this class, which somebody else defined, and would like to do a certain operation, I know how to do that. It's commonly used, for example, for sorting. So if you have IPv4 addresses and say, and need to sort them, you can say, hey, here's how to sort the IPv4 addresses, and then the sorting libraries work and so forth. We use Scala for all of our business logic. We use Python for glue code, and Python in some cases when there are attractive Python libraries, which happens with some machine learning cases, for example. So we need to bridge between Scala and Python. We still have the definitions in Scala. And since Python is dynamic, it can directly read the Avro definitions and say, okay, I now understand the structure of this data. We've taken this a step further, and from Python also defined the type or the schemas when we store these records in relational databases, which we use not for computation, but for making things accessible to the user. Or to applications. And you might wonder why we do that in Python. The reason is that the Python workflow orchestration, which we use to keep things together, is kind of the piece of software that owns the definition of the MySQL tables. So we can annotate, we use annotations here which propagate through the Avro definitions and go on, and then go out into MySQL. What we used to do was this in sort of explicitly define the same kind of schema as we would have there, but this is of course error prone because there's duplication between the definitions, and this took a lot of toil, took a lot of effort to keep these things in sync, and it's easy to make mistakes. We also use the fact that Scala and case classes is a stronger or has more expressiveness than the other alternatives for storing schemas. You remember we could store it as Avro definitions, we could store it as JSON schema and so forth. In those cases, you are limited to very few types. Scala has a very strong type system. So we use something called logical types, which basically says that from a semantic perspective, I have this one type, but when you store it on disk, you can store it as an integer or string or one of the basic types. And Avro has a little bit of support here. For example, it stores dates as integers with days since the epoch, and timestamps as long since the epoch. And there's a little quirk here that caused us a lot of pain, which is that the default storage of timestamps in Avro is millis since the epoch as long. And millis, as you might realize, is not always sufficient granularity, right? In computer system, things happen more like in microseconds. So if you have microsecond resolution, you can usually order most events, but millisecond resolution is not enough to order events in computer systems. So we prefer to store things as microseconds, but and that has caused a bunch of trouble with various Avro libraries. And at some point, I scratched my head and said, why did they choose millis? It's probably because Java chose a system current time millis, but why did Java use that? The only reason that I can think of is if you store dates way beyond the year of 294,000 something, then, or timestamps beyond that time, because that's when it matters to have millis and not micros. So I have a conspiracy theory that some time traveler had a Y2K problem, right, in this year and came back here to fix it, and that's why we are suffering. Anyway, we have our own logical types that we sort of define, and you could think of very simple ones, such as there's no concept of set, for example, in Avro, so you could store set as a list, and then read it up and assert that all of the items are unique, and when you get up to the case class, it's a set, so you have all of the semantics. You can have not only primitive times, but time intervals and so forth. And these are some examples, like year, month is something that we use a lot, but it has no Avro representation, so we say, okay, we just store it as an int, and then there's some other code that translates between them. And I said physical on the previous slide. This is something that we haven't had the time to dive into yet, but we had a production issue recently where we mixed up fields that had kilowatts and fields that stored kilowatt hours and tried to add them or compare them or something. And that obviously didn't work. And you know, these are different types, semantically speaking, right? And we have a great type system, so it should be a compile time error. And I used to grow up with C++, and there was this amazing library called Boost Units, which I never had the chance to use, which essentially concluded that all of the SI defined physical entities are actually 7 different dimensions. There's like mass, and there's length, and there's time, and there's energy and candela and whatever. So it had this powerful template library that would keep these apart, and if you multiply or if you divided length with time, you would get speed, and it would keep track of all of the types and so forth. And you can't do this in so many languages, at least not with static typing, but there is an odd Scala library called Coulomb that does this. I don't think it's possible to do with Java, but Scala has sort of sufficient strong type system. It's just one guy developed this Coulomb. So we're looking forward to sort of generate different types for kilowatts and kilowatt hours and store them as doubles on disk, and then as we read them up, get the right types and so forth. But we're not there yet. So, going into privacy. The way that we work with preserving privacy here in the lake is to separate the sort of the personal data from non-personal data, and treat them slightly differently. The things that are challenging in terms of sort of GDPR regulations to cope with in a data lake is the right to be forgotten, and then to have limited retention. Because if you have all of these data sets and the data is copied and it's immutable, and someone says, hey, please forget me, forget all the things that you know about me, this can be quite expensive to do something about, and it sort of breaks the whole sort of structure that we have. So we use something that I named the lost key pattern long ago, and it seemed to have stuck. It uses crypto threading. So for every record here, if you have some gray non-personal data, some red personal data, you take the personal data and you encrypt it with an encryption key. And you store these encryption keys in another table or in another data set. And this is kind of mutable in the sense that you don't actually mutate it, but you add new keys as new users arrive. And every once in a while, you take the request that of people that should be forgotten, and you remove their keys. So the data, personal data, is still floating around here encrypted, but you have forgotten about the key, so you can no longer use it. Not everybody uses this pattern, but a couple of companies do. For example, Spotify. So it has worked fairly well so far. One of the benefits is that you can pass this encrypted data around without any privacy issues. So some of the intermediate steps might not even know what the data is, and then only later, if you need it, you can decrypt it. This is a bit tricky to program these things. So we have a structure that we call shield formation, where we generate sort of derivative schemas and also jobs to transfer between them. So if this is the main schema here with the personal data, in this case, some kind of sale transaction with an ID that defines the human, sort of a customer club ID, in this case, and the store ID, which is personal data, because if you know the store ID, then you know where people have been, and that's very much personal data. And then some non-personal data, like what was bought and when was it bought, and so forth. What we do is to generate the classes, the corresponding classes where the personal data has been encrypted, plus a shield ID, and the shield is where the encryption keys are stored. And then you also generate an anonymous version where just all of the personal data has been dropped. And this is useful for a number of use cases. And the GDPR mandates that if you have use cases where you don't need the personal data, you're supposed to drop it sort of as quickly as possible. So this matches well to those requirements. And then we generate jobs that translate between these. So because this is all sort of boilerplate, there are lots of similar jobs that just differ by the schemas. It says Spark job here. We actually ditched Spark a few months ago and don't use it anymore, but you get the point. It's a batch job in some kind of data DSL language. And then the sort of flow is like this. Like if you get your sales in here, as data comes in, you generate these shields for all of the new user IDs that you see. You encrypt them here into this shielded job, and that's the one that you keep around forever. Whereas the shields, you append new users and you delete the ones that want to be forgotten. And since you do it there, this means that you can now keep this forever, and the whole, apart from this little shield, all of the sort of the model with immutability and so on works. If you need the personal data, you have an exposed job, and you can take it out to a system where it's stored in clear text. given that you do precautions here. And in many cases, you can just sort of have jobs that drop the personal data. And the precautions that I mentioned is that you need to secure the systems more ambitiously if you have personal data in the systems, basically. There are a couple of different ways of or strategies of partitioning personal and non-personal data, and these are the sort of the general patterns that I've seen. In some cases, I've seen people try to sort of scramble the data as it comes in and sort of not store all of the data, so and then hopefully you can use some of it. This doesn't work, and it's not so common anymore. In larger enterprises, it's common to see that you store a bunch of data, and then when you access the data, you apply lots of tight rules to see, does this user, does this application really have access to that kind of data? This is probably the most common solution out there. What we do is what I call a locked lake, where we store all of the personal data in the lake. In our case, both the shields and the personal encrypted data. In some variants of this, you store the shields outside if you want tighter security requirements on the encryption keys. But no humans have access here. So in order to do something, you need to sort of spit it out to another system where you have different access rules, and where in the case of personal data, only the people with that actually actually need to access the data can access the data. This scales to a certain degree. For very large organizations, it doesn't scale anymore, so the largest organizations have this kind of setup, but federated in different cells, maintained and governed by different teams. So if we apply that to that locked lake model to the shield, what the shield formation does, this is what's in the lake, where only machines can see it, no humans. If we expose something for a particular system that a particular team needs to see, they sort of own the governance here, and then there's usually some kind of green area without any personal data where it's completely democratized and anyone can access it. And in order for this to work and data to still be democratized and so that everybody can innovate, it's important that anyone can create jobs and deploy flows that work on this data, which is something different than for a human to access it. So that's permitted within the regulations. So with all of this schema generation from our case classes, what we've essentially covered is to get the best of both worlds with sort of schema on read and schema on write, while still being in the schema on write strictly checked world. So we know if we, for the part that we control at least, which is out to our clients, if we change something over here where the data is generated, since we generate everything, it will ripple through all the way out into the analytical databases. So we no longer need schema on read, basically. Back to this again. What I've presented to you here is a couple of things in which we sort of perform these steps, right? These are guardrails where we generate schemas to keep things in sync, to help with the testing and so forth, and to minimize operational toil by keeping the MySQL schemas in sync with the Scala job schemas and so forth. So these are steps that we take to sort of strengthen the software engineering processes in data engineering. And if you look at some of the trends out there in working with data, for example, the no-code and low-code, or the data measure, data contract, they essentially makes lots of these aspects more difficult. So we are clearly, the pendulum has swung way away from the industrial ways of working. The more blog posts you read, the further away you will get from what the sort of the data elite does. I have a little history of working with different types of companies. I was employed at Schibsted for a while, and we tried to do this huge effort and burned a gazillion Norwegian crowns. It was a very bombastic effort. It eventually, some interesting things rose out of the ashes, but it basically collapsed under its own weight. But now they are doing really well. I was at a large bank for a while, and this is not unique for that bank, but I've seen several banks spend about 2 years going from the decision we should have a data platform and a data lake to actually getting the first flow out in production. One of them, the Dutch Rabobank, actually went on a conference presentation and said, we spent 2 years and now we have the first flow and we are very proud. And then they came back a year later. We now have 3 flows and we are very proud. I can't find that presentation anymore. They probably took it down. After seeing these huge efforts, some of them are close, some of them are at a distance. This is my last freelancing project. This was at Bonnier News, where I said, maybe we can skip all of these huge technical efforts and just, be aligned with the use cases and try to get rid of as much technology as possible. Focus on stakeholders and use cases and see if we can get this industrial way of working without all of the technology. And this worked really well, and this is essentially what we have done since. So the things that I've shown you here today on killing the toil and removing friction and building on strong software engineering processes, they make a huge difference. From instead of spending hundreds of millions of crowns, we get up and running and build flows within weeks or months with 3 orders of magnitude less money. And if you compare these numbers and the number of data sets that we produce, we are not at Google level. We haven't done their investment, but we are at a similar level as Spotify in terms of number of data sets per employee or number of pipelines per employee, but without spending hundreds of person years in investment. That's roughly what I had to say. Questions?
Any questions? They all want to go on the data engineer course now.
Oh, yeah. Sorry, I used to do courses, but I don't do them anymore.
Bad luck. Not any questions? Then I'll shoot some. How come you came into this? To data?
Well, that was the sort of the first slide.
Yeah.
I realized from my journey at Google that this is where the future points. One of the things you get at Google is a crystal ball. You can see what the future holds for other companies. So I was very lucky. I came in on a banana slip, basically. And that's what initiated my interest.
Cool. How come data engineers or data engineering is behind software engineering? How come software engineering is ahead? Is it technology? Is it culture? Is it something else?
Software engineering is an older technology. I mean, the term dates back from the Apollo program. I think it was coined in the 60s. If you look at other disciplines as well, these factories that I mentioned, you have these now in software engineering. I mean, it used to be the case when I started working that you'd build a program you would type make my program or something. And if you go to my dad is also worked with computers. If you go to him and his colleagues, they wouldn't have make, right? They would type compiler, all the compiler flags, get an a.out file and use it. So when I started, we had these power tools called make and the compilers and so forth. But we have now, since then, shifted to factories, right? It used to be the case that we would make our program, SSH to the machines, install it, change a few config files, and okay, is it working, not working? Nobody does that anymore, right? We have a factory that, from the source code, creates a pristine container image built purely from source, and we don't ever mutate that image. Nobody does that. That would be madness, right? But we still think it's okay to mutate data, right? Even though we have reached this maturity in software engineering. So that has become a factory. And then you go to operations, right? Which is another field which is behind, is at about the same pace as data engineering, and you say, okay, I now have a blueprint in like Terraform or Pulumi, and that's okay, but how can I test it? No, you can't really test it because that's, cloud is not made that way, right? So you have this halfway, you have the power tools, but not fully industrialized. And then you go to security, and then even further behind, right? I think that 10, 20 years from now, we're going to think it's absurd to have these machines that run months after month after month. And if you get a breach, the attackers have a foothold in months or years. That's insane. Why don't we rebuild our machines all the time, right? Yep. Because we don't have a factory. Yep. So I think the older the discipline, the more it has gone into evolved into factory, and also building factories for all of these data and ops and security is completely dependent on software engineering. That's how you build the factories.
Yep. How much data growth do you get in your solution? Because if you don't mutate data, do you throw data or do you?
What I skipped over a bit briefly is that the raw data that we keep forever, but the derived data we can always rebuild. So that we have a sort of a retention, a lifetime retention window, which is dependent on the use case.
Of course. Anyone else? Yeah. We have a question in the crowd.
Where is most of the data that's being collected? Where is it kept physically?
In the heathen days, it used to be in Hadoop clusters, in the sort of the early data factories, and that would be on-prem installations. If you go to the banks, insurance companies, and similar, they are still to a large degree on-prem and still use Hadoop. For the rest of us, we have moved into the cloud. So it's stored in like S3 buckets, Google Cloud Storage buckets. That's the sort of the main lake storage, and then we use sort of managed databases when we need indexes.
Is there like a physical facility or something where this data is actually kept?
If it's on-prem, then either some sort of large enterprises actually have their own data centers. I mean, the bank where I used to freelance, they had these big mainframes in the basement of the building, basically, and all of these diesel power. That's very rare. I think Kivra here, I think is in a way on-prem, but I would guess that they don't have their own data center, but rent someone else's, rent space or rent machine in someone else's data center. And then it depends on where it is. Some want to be on Swedish soil. If you're in the clouds, that's usually an American cloud, and then you're rarely, sometimes on Swedish soil, but most often not. That's the thing with the cloud. You don't no longer care where it is.
You try to not care.
Something like that, yeah.
I was thinking, which library do you recommend to data analytics in Scala?
Within Scala, Spark is the most popular, so that's a reasonable way to start. We left Spark for reasons, but that's a good starting point.
I have one more question. If you're a data engineer, now you realize you have to learn how to make a factory. Where do you go? You go to Google, or you Google I'm a data engineer?
No, you need, if you actually want to learn,
Yeah.
you need to work at a place that has a data factory. So
Okay.
that's the only efficient school. Because you need to get in there, get your hands dirty, and be there. And I have.
Can you recommend some places?
Sorry, let me just finish last sentence. I have taught a lot of people that came into our team, and they teach them. And if they are senior software engineers or senior like BI developers, depending on which direction they come from, it usually takes about 6 months until they can teach the next person. And given that that is in a well-functioning factory environment, right? If you're outside that, then that time stretches to infinity. So you have to be in such an environment in order to learn it well. In Scandinavia, the most mature company is Spotify, by far. Then there is Klarna, King, Schibsted, Maersk. I believe that Goldman Sachs has some interesting activities here in Scandinavia, but they are not so open with what they're doing.
Nope.
So there are a few of these companies. We did some progress at Bonnier News as well. So that's where you learn it. The problem is that they are so few. So the knowledge, it's different in the US because they have been doing this in such a scale and for so long in Silicon Valley that it has spread much more to other companies. And that's why we are trying to figure out another way of collaborating so that we can bring this to companies that cannot attract the talent, the necessary talent, a critical mass of necessary talent.
Okay. Thank you very much. Again, yeah. Thank you, Lars, and thank you everyone for coming, and thanks again, Kivra, for hosting us here in a nice venue and very nice food. So that's it for the evening, and with that said, have a nice evening in the live chat, and everyone here, enjoy the rest of the food and drinks and everything. Yeah, thank you. Tack. Jag jobbar delvis konsultar halvtid på Vattenfall.